First screencast of the year where I'm going to do a tutorial of how to do some things. So in class we went over how to use graphical analysis. I gave you a handout that looks like this. It involves using graphical analysis, and then later on we're going to use a program called Logger Pro, both from Vernier Software. I think at least initially the graphical analysis you had to use as a Chrome web app or something like that. So I'm going to try to get back with technology and see if we can get that something that's pushed out or downloaded onto your devices. And anyhow, this is something to refer to. In order to actually access it, you would go on to the using, I think, graphical analysis or link to it. You would click on Chrome. You try to download it that way. We had some troubleshooting in class, which happened, which should help us out. So if you weren't there, that may be something I need to help you with. At any rate, I'll go through how to do this in a couple of examples. I gave this out in class, and we went through these two together. I'm going to do that again here, and then I asked you to pick it. Oh, I think I did only 5 instead of 6, so maybe I only printed out 5. That's interesting. I don't know why that 6th one didn't go. At any rate, I asked you to do 2 at home and either screenshot them or save them so that I could see them. So I want to make sure you can do at least a couple. This is the initial shape of the graph. This is the linearized version of the graph, and this is the mathematical equation. If you remember, the mathematical equation should look kind of like this, graphical method summary. So when you linearize something, you're going to start off with a y equals mx plus b is our general formula, but we don't use y's and x's. We use the y-axis variable and x-axis variable, and we have the slope with units. But if you want to linearize something like this column will tell you how to do it. This column will tell you how to represent things algebraically. So super useful. All right, so what we're going to end up doing is we're going to go ahead and do these 2 sets of data and enter them in. You can follow along. I also will upload something like this, a little bit of a reading about graphing and linearizing and stuff like that. Okay. All right, so first of all, you're going to find wherever graphical analysis is. Again, hopefully at some point you're going to be able to download it. You can put it on your phone, to be honest with you, so it's a free download. So if not, again, you can use it as a Chrome web app, I guess. So when it opens up like this, if we're not hooking up sensors and we don't have them yet, we're going to click manual entry. The first thing you're going to do is you're going to click up here and go to column options. So for this, we're going to be plotting out drop height and bounce height. The independent variable is on the x-axis, so that's going to be drop height. We did a lab with this in my regular physics class. I'm going to say centimeters. You can leave this for right now, be auto, not a big deal. However, when I look at the data, I notice there are no decimals, so I'm going to click that as 0. I'm going to apply that. Over here, I'm going to do the same thing, column options. This one's going to be the y-axis value, so that's going to be bounce height. Units also are centimeters. With this one, I had the data up to 1 decimal. Okay, so now I'm just going to go up here and type in the first piece of data. I had 100 centimeter drop height, 87.6 centimeters bounce height. And I just keep hitting tab as I enter this data. Now, notice I don't have to put it in order. So like if I actually do something wrong here, or do it differently than the sheet, and I put 0, 0 in, okay, doesn't matter. It'll automatically graph it. That's what's so nice about this. Cool. Now this looks like a super nice linear fit, and it's scaled to 0, but I want to make sure it is always scaled to 0 for right now. So if you go under here under graph options and then scroll down, edit graph options, you can give the graph a title. So I'll say bounce height versus drop height. And this scaling looks pretty good. I always like to include 0. I always like to include 0 here. Also, I don't like to have the points at the very end, so I'm going to make that up to 100. I'm going to leave this 100, but you could honestly make it 110 if you want. But I guess I can leave that 100. So that's fine. And we're good. We can just X out of that. So at this point then, that looks like a nice graph. I'm going to go down here again to graph options, and I'm going to apply a curve fit. For a while, we're just going to use a linear fit. There are a bunch of other fits in there, but we're going to use linear. So I'm going to apply that, and lo and behold, it looks great. I can move this dialog box around by selecting it, holding down on the trackpad, and then moving it over. I don't think I want to do that. So this has a y equals mx plus b general formula. The higher the r value is, the better your data. The lower the root mean square error is, the better the data. Normally we would want an r value of 0.96, 0.97-ish or above. This is 0.9999, so that's fantastic. This is a little more problematic. I really use this when I'm comparing which fit to use. And if I'm comparing several different fits, the one with the lowest root mean square error will be the one that I would choose. So in this case, instead of y equals mx plus b, I need to convert this to the mathematical formula for the data we have. So that's going to be bounce height equals the slope times drop height. And this b value is 0.55 centimeters. In my mind, it makes sense that that should be a 0 y-intercept because 0 bounce height gives 0 drop height. It's really only our uncertainty that causes this to happen. So if it makes sense that the y-intercept is 0, it's reasonable to assume that it is. And in fact, you could even plot the points in there like I did to sort of force that. So in this particular case, if you look on the sheet of paper I gave you, it says BH equals the slope centimeters per centimeter. That's going to be 0.87 centimeters per centimeter times drop height plus 0 centimeters. And you can save this as something like a trial 1, know where you put it on your computer. Okay, so I'm going to cancel that because I do not need to save this. I've already saved it over here. So now I'm going to do a new experiment. That means this data will be deleted, and so I need to be careful about that if I did want to save it. I just recommend you screenshot the ones I ask you to do. So don't save. Again, going into the next one, this is going to be sample set 2 on that same paper that I showed you, which is this. So it's this data over here. And I'm going to click on this. The x-axis is going to be cross-sectional area. So column options, cross-sectional area. The units are millimeters squared. Now there's no superscript or subscript button, so the way you show a superscript is to put a caret. That's you hit shift and the number 6 on your keyboard, and then a 2, so that says that it's squared. Again, with this one, I don't think I need any decimal places. I'm not that concerned about the displayed precision at this point. So I'm going to apply that. Then I'm going to have this one be resistance. That's going to be in units of ohms. And again here, I think I went to 1 decimal place with the data, so I'm going to continue with that. So I'm going to type things in. And I had initially 20, and then 2.0, 18, 2.2, 16, 2.5, 14, 2.7, 12, 3.4, 10, 4.0, 8, 4.9. So you see this is a very different pattern than we had before. 6, 7.4, 4, and 10.3. And then finally 2 and 19.5. Okay. And by the way, if you type something wrong, like say type this was 27, puts a data point up there, you can see it pretty quickly. So you can go back and retype that. So I'm going to go over here. I'm going to go to this dialog box, this graph options box, edit the graph options, title it resistance versus area. I'm going to scale this from 0, always show 0, and I'm going to scale this one from 0, always show 0 as well. There is no right axis, so we don't need to worry about that. Okay, so that looks like some nice data. I mean, very nice data, actually. If I want to apply a curve fit now and try a linear fit, that does not look good. So if I apply that, you notice, not a good fit at all. Higher root mean square error. This R value, it's negative because the slope is negative, but it's 0.827. That's not good. So we don't really want that. Now, you might think that what you would want to do is look at, say, another curve fit. Like, for example, probably looks like an inverse curve fit. That's nice. But the problem with that is it's hard to use this graph to make a prediction. So we want to actually create this to be a nice straight line graph. By the way, if you ever have an outlier and you want to plot a curve fit or a line without using all the data, you could select part of the data and actually do curve fit just to that. Okay, just as a heads up. Okay, so what I want to do now is I'm going to create a new calculated column. And when I look at my graphical methods summary, nope, not the graphical methods reading, but the graphical methods summary, the graph looks like this. So in order to linearize the graph, turn it into a straight line with a positive slope, I need to graph the y-axis variable versus 1 over x. And instead of y equals mx plus b, I'm going to have y equals m times 1 over x plus b. And that'll allow me to make a better prediction, because a straight line graph really can help you make a prediction. Okay, so in order to do that, I'm going to go to either of these two columns, doesn't matter, and I'm going to click Add Calculated Column. So since I want 1 over the cross-sectional area, because I'm going to plot resistance versus 1 over the area, I'm going to say that. My units are going to be 1 over millimeters squared. I'm going to probably go to 1 decimal place again, and I need to insert an expression. So the question is, what do I insert? Well, it should be something over something else. That's an inverse relationship. This something over something that you can take to an exponent could be for an inverse square relationship. This could be for a square relationship, something like that. So I'm going to click this. So the parameter A is going to be 1 over, and then I don't want resistance here. Maybe I should have chosen the x-axis variable, cross-sectional area, but if you notice, if you click on it, you can choose either of these. And now, if you scroll this over, there's nothing else there. So this is a little sneaky because it doesn't seem like it does something. There may sometimes be something else over there. So I'm going to do that and apply it. Ta-da! I've got a new column of data. That's fantastic. Not only goes to the 10th, so what I may end up doing, column options, I may go to 2 decimals here. I don't think it's going to matter because I think the computer stores that, but no worries. All right, so the problem is the graph didn't change. Well, I can click on either of these axes, and I can choose what I put in each place. So in this particular place, I want 1 over the area. And now, lo and behold, it's a straight line graph. So I can go apply curve fit. I'm going to apply that. And it's beautiful. I've got a 0.9985 correlation. And the root mean square error is very low. And the slope, 39.31. So the way I would write this is I would say, I go in the format. Ugh. It looks like this. Okay, so I would go and I'd say resistance equals the slope, 39.31, ohms divided by 1 over millimeters squared, which is weird units. That really means ohms times millimeters squared, end parentheses, and then that multiplied by 1 over area. And my y-intercept is 0.1329, so I'm going to call that 0 also. So resistance equals 39.3 ohm millimeters squared times 1 over area. And that would be my equation for this. So I hope this helps. Yeah, hope it helps.